In the last few videos, I've talked a lot about geometric sequences and series. In this video, I wanted to talk about the sum of an infinite geometric series, a shortcut for finding the nth partial sum of those, and also kind of looking at, well, an infinite series, when can it converge? But really, the most important thing for today is just looking at the nth partial sum formula and kind of examining these shortcuts. And these are often used in finance and a lot of different places for figuring out things what are called like annuities or perpetuities, an account where you would say like a retirement savings account. Say you were to save $100 a month and you're saving that into your retirement account. Well, as you're plugging that money in, you're also contributing to the overall balance. That balance is growing based on an established interest rate of your account, which is the reason why you want to have savings, because not only are you saving money each month, you're also going to be generating interest upon that. And so it's so valuable, but basically it forms the pattern of a geometric series, because like each month you're plugging in $8, and the prior month's amount, and sometimes this is referred to as present versus future value of an annuity if you are putting it into financial terms, is basically just the previous month is you put in an amount of money, but you've also gained some interest based on the interest rate. And then, each month you're gaining more and more money because it's growing based on interest. And it has these sort of mathematical formulas. And basically there is a shortcut for determining the sum of the entire amount, which is, often what we call the present or the future value. Anyways, but basically, how do we start? How do we look for the shortcut formula? And actually, it can be done by examining the pattern of the nth partial sum, S sub n. So, like, say we're looking at this infinite series, and we wanted to say, well, what is S sub n? What's the nth partial sum of this geometric series? And remember, it's geometric, meaning that it just has a starting term A and a common ratio R. Each term is getting bigger by multiplication by R. Or again, it's like an exponential function. Where this is the basic formula for a geometric sequence, meaning we're going to be adding it up forever. And usually in financial terms, you're not doing an infinite series, but you can actually, that's what's sometimes called a perpetuity. Anyways, basically the nth partial sum will just be, instead of being the infinite series, it will stop at the nth term. So the first term would be A, the second term would be AR, then AR squared, and so on and so forth. And basically, instead of just writing the dot dot dot, how you could write that it stops is you could say, well, it's going to eventually go up to AR n minus 1, then we're going to stop at AR to the n. And actually, I misspoke, because AR to the n is technically not the nth term, it's the n minus 1th term. This would be the nth term, because remember, the first term has 0 exponents, the second term has 1. It's always 1 less, so actually I don't want this. And actually, but what I could also do is, if I wanted to write a couple more terms, I could actually write it as ARN minus 2 up until ARN minus 1. And you'll see why I'm doing this in just a minute. And in this particular case, basically this is going to be the last term of my nth partial sum, because this is the general formula for AN, right? And that's the last sum. And the one before that would be 1 less, n minus 2, and so on. Obviously, since I don't have particular index numbers, right, I'm not actually plugging in 1, 2, or 3 in the end. I don't know how many terms I need, but this is kind of how I can describe, okay, I'm going to need some number of terms starting here, ending here, and I'll just put the dot dot, the ellipsis in between. So why are we doing all this? Well, let's say I examine the nth partial sum, which is just a sum of n payments, or n, geometric series options in this case. So like if I was putting this back into context to an example we've looked at in this lecture series, it'd be kind of like looking at the 1/2 example, where I could look at the series as adding up each of these fractions: 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. And this is kind of what I'm imagining here. Well, since there's a common factor, I could think about what happens if I was to actually multiply the whole thing by R. Like, let's just say I'm going to take R and multiply through by the entire series. Sorry, my tablet is not behaving. I'm trying to click it so that I can actually write. Okay, there we go. But if I take R and multiply through by the nth partial sum of the geometric series. But basically, if I took each term and distributed through by R, well, this would leave me with A times R here. The next one would be AR times another R, which would be AR squared. The third term would be A times the third R, another R. And basically notice that each term would just multiply by a factor of R. And it would actually be almost the exact same series, where if I had AR to the n minus 2 and I multiplied that by another R, that would be AR to the n minus 1. And if I took AR to the n minus 1 and multiplied by another R, that would just become AR to the n. Because that would basically just add 1 to the exponent by rules of algebra. And here we go. So, well, why am I doing this? Well, if you actually examine, well, what's the difference between these two series? Notice that they're all almost exactly the same because they all have exactly the same terms, right? When I multiply through by R, almost everything is the same. The difference is this one has an extra A in front and this one has an extra AR in bottom. So if I actually took the difference between the nth partial sum and R multiplied by the nth partial sum, that would be synonymous to subtracting these two things from each other. And if I was to subtract this from this, basically AR, well, this one would cancel that one, this one would cancel that one, this one would cancel this one, and AR to the n minus 1 would cancel this term. And basically every term in between would also cancel because that's we don't know how many terms are in here, but it's a pattern starting with A, ending with AR to the n minus 1 and everything in between. This one has all of those same this is exactly the same pattern because I just took everything and multiplied by R. But the first term is missing and I've gained an additional term. So what I'd be left if I actually took the difference between S sub n and R S sub n, I'd be left with the first term from the first one minus AR to the n, which is the last term from the last one. And again, this is kind of strange and you might be wondering why we're doing this, but the point is we can actually solve for what is the nth partial sum of a geometric series S sub n. Because notice that over here S sub n is a common factor in the left-hand side. And if I factor that out, that would leave me with 1 minus R. And actually A is a common factor on the right-hand side as well, which would leave me with 1 minus R to the n. And then I could solve for Sn by dividing by 1 minus R. So this would leave me with the formula A multiplied by 1 minus R to the n over 1 minus R. And this is the shortcut formula that I was mentioning that exists. And basically, what does this mean? If I want to find the sum of the first n terms of a geometric series, that's exactly what this stands for, right? S sub n. It's always equal to the first term times 1 minus R to the n, that's just the nth term, divided by 1 minus R. And so let's do an example. Let's say back to this problem, we wanted to find S5 for this geometric series. We could do that by applying that same formula. So in that case, the formula, again, let me copy it down, is A times 1 minus R to the n over 1 minus R. I would just need to plug in those things into here if I wanted to find S of 5. So S of 5 would mean n is 5. A was the first term of that series, which was 1/2, multiplied by 1 minus R, and R was also 1/2, raised to the n power 5, divided by 1 minus R, 1 minus 1/2. And so in this case, it doesn't exactly seem simpler, but 1 minus 1/2 is 1/2. So I would have 1/2 divided by 1/2, those would cancel. And that would leave me with 1 minus 1/2 to the 5th power. And 1/2 to the 5th power is 1 over 32. And notice that 1 minus 1 over 32 would be 31 over 32. Because this, I would need a common denominator. And kind of as I was describing over here, what I ended up having is the opposite fraction to 1 over 32, 31 over 32, which is just the difference between 1 and itself. And it's sort of a different way of thinking about it, but it's a cool shortcut, meaning that I don't need to go through this incessant pattern of adding up a bunch of fractions as we did a couple of videos ago. There is a shortcut, and that is the formula for it. And finally, the last kind of implication about this is if I want to know, well, what happens if I keep going, and actually the little formula got cut off. This is only if R is less than 1. This is something that you don't need to worry about because we're not going to worry too much about infinite series in this class. But you know, in some classes you would be concerned with actually finding the sum of an infinite series. We could think about what actually happens as this pattern continues, as the series goes to infinity. You could write that as S infinity, but that would just be an unrestricted infinite series of sums. And basically what would happen is we'd be looking at what happens if n goes to infinity, and that would specifically would only converge in the case when it was a fractional ratio. Like in the Zeno's paradox example I was talking about in the previous video, I mentioned that, you know, this the series of fractions, since it's getting smaller and smaller and smaller, could actually converge to a specific case. And basically, in the context when the ratio of the geometric series is less than 1, meaning that it's a fraction, it's getting smaller and smaller, it will actually always converge. And basically what happens is actually r to the n will always approach 0, and we'll be left with even simpler formula, a over 1 minus r. And so you can actually find the sum of infinite geometric series using this other formula. Anyways, again, not something you need to worry about, but I figured I would just at least introduce all these concepts and sort of see how that plays back into this proof. Anyways, also, it's interesting to note that arithmetic series also have a similar shortcut formula for finding the nth partial sums, but I don't think we need to worry about that. It's not as relevant to much.